Thank you, and sorry for the delay. We had a technical issue, and thank you for being here today with us. I present myself. I am Fabio Masci, the founder and lead executive officer of the Edge company. Today, we are going to talk how can computer vision enhance safety in the aviation sector. We start from the problem we are trying to solve, the bird strike. You should know that every 15 minutes there is a bird strike worldwide. Every aircraft at any airport, at any location, usually have the risk to hit a bird during takeoff and landing especially. And you may not know that the bird strike is old as the aviation is, because the first bird strike was taken during the first flight by the Wright brothers in 1917. Today the problem is not solved yet because as the Civil Aviation Authority reported last year, we had an increase of 260% and more strikes in the wildlife in 2020, regardless the fact that in 2020 we had a decrease in 70% of flight worldwide. This was related to the fact that, of course, due to the pandemic, people did not survey the airport, so wildlife took again priority on the space. Actually, methods that are used are people, the so-called speak bird control units or radar, and usually to disperse the birds, the most common device used is the gas cannon at airports. But this is usually not good enough because as we said, the problem is still out there. So we are talking about our system. We developed this using artificial intelligence for the first time to identify, track, count, and classify bird species in order to enhance flight safety at airports. The BCMS venture is an integrated system, distributed system that uses different sensors distributed in the airport in a way that can be covered the entire area of responsibility, especially for the landing and approach path to assure a safe landing and takeoff to airport. This was born in late 90s when I was chief of flight safety, and introduced a method together with a team to counter the bird strike issue. And the method was so successful that we had a reduction on 70% of bird strike after 1 year implementation, and the Italian Air Force decided to extend this to the entire Air Force. From that, we start developing our solution, applying deep tech technology, using sophisticated algorithms developed by Italian university, Italian researcher, and using hardware like NVIDIA and Lenovo hardware to maximize the performance of our system. It is important to notice that the European Civil Aviation Authority, EASA, determined and published a roadmap addressing the possible implementation of artificial intelligence. It is interesting to notice that there are 3 steps basically. The first steps by 2021 was aiming to have a system that could have helped people in taking decisions. The second step in 2022 to have a system using artificial intelligence that allow cooperation between man and machine. Then we go to the third step by 2024 to have a complete autonomous solution, taking decision and making action by itself. The BCMS venture actually is already at step 3 in 2021, since it is able to take decision to low, medium level, take action, and in theory controlling automatically the dispersal system. So it's a complete autonomous system able to do detection and even dispersal of birds. And this is how the system works. Basically, you have different cameras.
For birds to live. However, they represent a big threat for airplanes. The bird strike. The impact between a bird and a plane happens mostly during takeoff or landing, the riskiest flight procedures. Current monitoring systems don't provide the required answer. The number of bird strikes is still increasing, and a new dangerous threat is arising. Little commercial drones used to disrupt both safety and security. Venture is the next generation bird and drone detection system. The first system which uses artificial intelligence to detect, track, count and identify the location of birds and drones, and above all, classify bird species. Intelligent cameras equipped with our machine and deep learning algorithms constantly sweep the airport area. A combination of our algorithms and high-efficiency cameras, 5K and above, allow extreme precision and long acquisition range. When a bird is detected, a warning will be issued and an alert appears on the situational awareness display. While camera 1 and 2 continue sweeping the airport area, cameras 3 and 4 will be clean, the final path before takeoff and landing, to provide real-time situational awareness to the pilots.
Well, now we dig a little bit deeper in the secret of this beautiful system. First of all, we are using hardware, camera, Bosch, and there is a network infrastructure. Preferably, we are looking for optic fiber connection, but we can use radio links. The minimum required capacity is 140 megabits per camera. Then we use a Lenovo server with NVIDIA card inside. This is a great advantage because originally the system needed 3 different servers. And then with one single server with virtualized machines, we even make the system implementation easier. Then we're using NVIDIA card, specifically the RTX 4000 and the RT 404 that can manage up to 4 cameras at the same time. How the system works, so we have the first machine that is a video analytic processor that analyzes video stream of up to 4 cameras. Then we have a data manager. Even this is a virtualized machine that stores detect events to a database. We have a video management system that stores and records a video from detection. And then currently VAP and the 3 machines again are virtualized and running on an Lenovo SR660 server. Multiple agents can access to the system to different secure connections through REST API. Basically, the system has 3 different levels of analysis. When a bird or obstacle are detected by one of the camera, the system creates an event. Each event includes species, class, number, location, direction, speed, and timestamp. The video streams from a camera are constantly feeding the video analytics pipeline to check for different events. The detection modules detect any moving object by using a background subtraction algorithms. Clean detections using some morphological filters. Filters detection applying shape constraints. Tracks detection between multiple frames to create trajectories. And then this allows how to predict the movement of the objects even when temporarily occluded. This is typically happening when a bird flies against a strong or typical background that is similar to its colors. Then what happens? The compute tracks features and classify the tracks in a different classes. For example, when we decide that this is a bird, we decide that if a bird is standing on the ground or is a flying bird, then we remove all false tracks that not correspond to birds. Then we go to the core of the system, that is a classifier. We use a custom convolutional neural network to classify if patch forming the track. We combine the classification results for each track and assign it a species on a global confidence score. We use a prior information because the system doesn't use just computer vision but uses a priori information to better and enhance the classification. And then the species classification is a very challenging task because it's very extreme varying lighting condition. The pose of each bird can be different, and the size of the smallest patches, which is 32 by 32 pixel. We combine every kind of possible information retrievable from videos, shape, color, movement with historical prior date. And as we collect more data from airports, the system learns and improves itself. Then we assign a 3D world location using GPS coordinates. We group detection into events and then assign each event in a quadrant of the airport map grid for visualization and risk assessment. Different colors means different risk. The closer you are to the runway, the biggest is the risk that an impact can create. We did testing on real life site. Was an airport in the north of Italy. There was a partial installation using just 2 sensors and with a computational units that was connected through radio links. The objective of the test was evaluate the capacity of the system, to detect birds and obstacles, and make a confrontation with the expert bird control units at the same time. For the testing, we evaluated more than 130,000 tracks for a total of more than 2,500 hours. And we did run the test for about 60 days. And this is the location. The 2 cameras had almost a coverage of 30% of the airport. Some part of the cameras were occluded due to obstacles. And we created an intersection area where maximum was the efforts of the BCU and maximum was the coverage of the system. Basically, after these 60 days, we collected data that allow us to say that the system was able to detect birds with a 93% of accuracy, with 7% of false positive tracks. Among that, 95% of these tracks were other animals and little insects. Of course, once the system is running and acquire more information, the system will improve. We estimate that after 12 months of implementation, we can reach a true positive rate well above 96-97%. This is the comparison between what the man can do compared to the machine. Basically, after 60 days, the system saw almost 60,000 tracks, while the BCUs saw 7,400 tracks, birds. That means that the system is capable of seeing more than 7.5 times more than the man can do with the same condition. Then we analyze the capacity of the system to classify the bird species, and those are the results. The methodology used was to compare the 6 species with which the system has been trained and see when the system was classifying correctly among these 6 species. So basically, we have an average accuracy of 94%. The difference between different species depends on the data we are available and to train the system. One of the biggest questions was how the system perform with different weather conditions, with low visibility, with bad weather. Well, we had a good, beautiful surprise because in a bad weather condition, actually the system perform way better than the man. And we get even 8 times more capacity to see birds compared to the personnel working for the BCO. Actually, in the world, we have more than 17,000 airports, and in summary, what we see that the system is capable of having a detection and tracking capability of 93%. The BCMS Venture is capable of positioning the birds in a 3D environment. We have more than 90% accuracy in classification, and we shortly introduce a dynamic risk index that will be pretty useful for people operating as a BCO. Of course, the system is completely green since we are using a passive sensor, so it's compliant with ESG parameters. But it is important to understand that we start the developing of the system for airports, but we are ready for the new reality, because shortly everybody will have knowledge about the urban air mobility. Urban air mobility is the new way people will move around the city using electric drones in the future, for now piloted. If safety is important at airports, it will be even more important at cities. So if we can even kind of accept that an aircraft have a damage during a takeoff from airports, we cannot surely accept that a drone will crash downtown in a big city like Paris or Rome or Milano. So basically, we are discussing with players, we are discussing with authority, and we discovered that our system perfectly fits with the requirements of assuring a control and constant monitoring of the airspace, detecting possible obstacles that can jeopardize the drone activities at town. And another important aspect, that drones are an incredibly opportunity for the market development, but represent an important threat. This is why the BCMS is an important actor to play against drones, since it is capable in detecting in a very accurate manner drones too. In summary, the BCMS is a family of obstacle detection system using a well-balanced proprietary technology melded with experience that created a solution that is resolutive and especially cost-effective. I thank you, and I'm still sorry for being late today. If there are any questions, I will be more than happy to answer.